We are interested in complex hierarchical tasks which have a latent structure. These tasks have many practical applications, such as cooking, surgery, assembly, and driving. We attempt meta-learning to achieve generalization in complex hierarchical tasks. Ideally, we want to be able to complete an unseen task with a single demonstration. We present Neural Task Programming, or NTP, a meta-learning algorithm for addressing the challenge of generalization in complex hierarchical tasks. We show that our model is able to generalize across several metrics, is data efficient, and works in settings with varying input states and low-level primitives. Here we see NTP take as input a demonstration of a new block stacking task from simulation. NTP instantiates a task condition policy that interacts with the real environment to complete the task. When applied to a new task, NTP takes a single demonstration of that task. This demonstration can come from any domain, including simulation, VR, or a real robot. The output is a task condition policy that interacts with the environment to complete the task. This policy comes in the form of a hierarchical neural program, which at the lowest level calls robot APIs to interact with the environment. Here we see a detailed rollout of NTP in the block stacking task. We see that it begins with a high-level program of block stacking. It outputs that the next step should be a pick and place program. Pick and place is then reduced to a pick and then a place. The pick program is further decomposed into a move to program and a grip program. These are primitive programs, so NTP predicts the arguments that the primitive program should take. This first primitive program, move to, takes as input the blue block and proceeds to interact with the environment, executing that primitive with the specified argument. Then the grip program is run, which is again primitive, so it also takes the argument of the blue block. After interacting with the environment, the pick program is now complete. A similar decomposition occurs completing the place portion of the task until NTP predicts that both place and pick and place are complete. Note, whenever a subprogram is called, NTP also predicts the relevant subsegment of the demonstration, so subprograms only see the portion of the demonstration that pertains to their functionality. We highlight that NTP is a closed-loop feedback policy and thus able to recover from intermediate failures in the task. In this example of the block stacking task, we see the blocks get knocked over in the middle of the task. Given the state input, NTP realizes that it needs to return and redo the previous components of the task. NTP generalizes across tasks in three types of variation: task semantics, topology, and length. Tasks with different semantics will explicitly have a different goal. Tasks with different topology will have the same goal but have a different method of achieving that goal. Tasks with different length simply operate on more objects. Here we show NTP evaluation in the object sorting task. Like block stacking, a single demonstration is generated in simulation and the task condition policy is evaluated on the real robot. In object sorting, NTP is trained with only one instance of each object, but tested on multiple. In addition, we explore the task of table cleanup, which combines skills from both stacking and sorting. The goal is to sort forks into a single bowl, then stack the bowls for removal. In this task, we see generalization in the form of topology and length variation. While NTP may predict the correct operation, the execution may still fail due to primitive failures.